and that has many different variations to it. So we'll probably spend 1 or 2 lectures just on the what's called the mechanical system for buildings.
Now, so announcement. The design project part 2 is posted. So I highly encourage you to try and install the software that you're gonna need. So if you run into any issue, you can reach me and we can solve it together. And especially for the people who doesn't have Windows on their computer, there is like a PDF on Canvas with several options. Please at least try the first 2, which is one is the Oporto GPU desktop. I don't know if you are familiarized with that, but just follow the instruction and let me know if you have any questions, okay? Just test it and make it work.
Yeah, so now on it's even more important that you start your homeworks and design projects early, because some things you cannot solve in 5 minutes or 1 hour or 1 day. So you have to start early, meaning as soon as the design project is out, you try to tinker around with the software, say, okay, software is working, I can now take a step back and wait a few days and do the rest of it. So don't wait until the last day to start a project, because you may get in a situation where you get 0 points basically, because you can't do it, you cannot run it. So make sure you leave time for those unforeseen circumstances. All right, so mechanical systems. So many people think that what mechanical engineers do is mechanical systems. Like they think, oh, mechanical engineers fix elevators. Mechanical engineers fix air conditioning systems. And of course, that's wrong. Mechanical engineers, they build many different things. They build rockets, cars, health technology. But in the public mind, mechanical often is attached to these more technician type jobs that are done by non-mechanical engineers, because you don't need that much training for those types of jobs. So here, same thing, it's called a mechanical system. And there you go. But it's usually only you're involved in that in the design of it, because that requires calculations like the one we've done, and then once it's operating, then usually it's operated by facilities maintenance personnel in buildings or companies like Siemens or Johnson Controls. They have technicians who are familiar with these systems. So there's lots of things to talk about. This is just a brief overview of some of the elements that are important. So one is zoning. Any idea what zoning means? Usually zoning means that you have different neighborhoods in a city, like one zone is residential, one zone is commercial, but this is within a building. Yeah, what does zoning mean?
It's like how specific your control of the environment is, like whether it's a room by room thing or the whole building at once.
Yeah, so it's how specific your control is to the environment, so whether it's a room by room or whether it's for the whole building. Yes, that's right, and that's very important in both energy use and in the engineering of buildings, that commercial buildings have always multiple zones, meaning that this classroom is one zone. So there's one thermostat, there's one controller that cools this classroom, and then an office wing next door will have a different zone. So basically you can adjust the ventilation rates, the heating and cooling for each of these zones. Why is that useful? Why do we have a different zone for this classroom versus an office wing next door?
Yep. There's like different temperatures, so different cooling needs.
Different cooling needs? Why do we have different cooling needs? And it's the same city, right? We're all in San Diego. We all have nice, cool air outside. Why is different cooling needs?
Because like in this classroom, we have more people than that might be unoccupied, so we don't want to make that
right. So we have more people in here, right? So all of you generate energy, generate heat, and that heat is per square foot of floor space is much more than an office next door where there's one person in a large office space, and some are even unoccupied. Which means if you have one airflow that would go to both rooms, then basically the office would be way too cool, or this room will be way too hot, depending on how you adjust it, and so you cannot maintain a comfortable temperature in both zones, both office and here at the same time. So you separate those out, which means that whatever happens in the office is completely independent of what's happening in here. You can adjust completely independently how much cool air is going there versus going here. At your home, unfortunately, they're very rarely zoned, which means in your home you often have a single thermostat for the entire house, and that's the only place where temperature is measured, which means that if you have a multi-story house and you have bad insulation in the attic, what happens to your house during the day? Many stories, you have insulation, attic that's bad, so which part will be hotter of the house?
Top floors.
Top floor will be hot, right? Downstairs will be cool. Now your thermostat is at the bottom floor. So thermostat senses, oh, everything is fine, right? Building is cool. And that's because you have one zone, so you have one measurement, which is not accounting for all the differences you have in the building. Well, you should have two zones, one for the top floor, one for the rest of the house. That means now the thermostat can tell, okay, this room is hot, I need to send cool air to that room, but not to the room downstairs. Unfortunately, in homes, because we want to cut costs, they don't zone most homes, and so you waste a lot of energy because you're cooling places where you aren't even there, or you're cooling places where you don't need to cool them because they already are cool as is. So zoning is very important. It requires a lot of thought in buildings. And heating. So we'll talk about heat pumps or furnaces. I won't go into detail right now, but different types of devices that can heat a home. Cooling, we'll talk about whether these devices that heat and cool buildings are local or non-local. That means some air conditioners are local, meaning that you have a through-the-wall air conditioner or through the window. So a little box that goes through the wall, and basically it is everything in one place. It has a thermostat, it has the ventilation, and it has cooling and heating all in one box. That's local. Whereas non-local means you're ducting air around. So there's somewhere else in the building is a boiler or a condenser, and then you need to duct the heat and cool air or water around to get to the place where it's being used. And then there's other types of conditioning of air. So we don't just care about hot and cold. We also care about, do we have enough fresh air? So we talked about COVID, right? So COVID means that we only use fresh air in buildings these days. We no longer recirculate the air. So we need fresh air supply. And we need sometimes humidification, meaning that the air is too dry. We don't want that either. So we want to add humidity or remove humidity. So both ways, that's another metric of air quality. Right, so we'll talk about each of these things some more, but here are some examples of different types of ways of heating or cooling buildings. So here is what I just talked about. That's the, sorry for the bad resolution here, through the wall unit. So that's the little box that you often see in all the buildings where you have just a single room being supplied by cold or warm air coming from this little box. So it has a grill in the front. It has an outlet for air to get out on the front, and then out here it has a fan to remove hot or cold depending on the heat. So this can ventilate, it can generate hot and cold air. It's everything in one box. That's why also these are called the packaged units, because they're all packaged together in heating, cooling, ventilation, all in one place. Then in another more modern or expensive homes, you have this type of a setup. So this is now principle the same type of home, two-story home, but now you don't have these local solutions, but you have what's called a central or a forced air system. So forced air or central system. And you see, look at real estate listings for houses, then one element will be what's the heating and cooling, and it may say forced air. Forced air means that you're forcing air through ducts to go around the house. So in this case, you would no longer have to penetrate the wall with these local devices. but you can be smart when you design the building to basically route the ducts in the walls so nothing is visible except for a little grill in the ceiling, a little grill on the floor. Just like here in this building, we have these grills on the ceiling and the floor. And then you just need to think about how do I route all of these air inside and out. So you have to have what's called a return flow, meaning that you suck the air out, you return it to the central plant, and then you have a supply flow. Supply flow means you take the cooled or heated air and you supply it to the rooms. So here is supply that goes in, and then here's another supply also goes in. Maybe 2 rooms here, so you have 2 supplies, or maybe the building is too large, so you need want to get more comfortable quickly. And then here is the return, where you take the air back down to the basement. In California, we don't have much basements, so in our case, it's a little bit more tricky. But in other states, usually all of this equipment is in the basement. That's nice because it's not particularly pretty equipment; it's ugly equipment. And requires a lot of space, and so we can put it away in the basement where it's out of sight. But in the basement, you then will have different types of equipment that will provide the heating and cooling to this home. So for heating is something that's simpler. Heating has been around for tens of thousands of years because we've been burning wood or burning oil and other things. So heating is simple. Heating, you just make a fire, right, and you burn something. We have over time become more interested in sustainability, so we moved from coal to oil, moved from oil to gas, and now we're moving from gas to electric heating. And so down in the basement, that means things changed over time. We may have had a coal storage room in the old days, then we had an oil tank, then we had a gas line to come from the street, and now we just have electric power going on there. But it's one place where you generate fire, and then you basically take the air that's coming down here, you heat it, and then you bring it back up, and then it will cool in here because we're losing heat to the outside. So it'll get colder in here, then you get it back down, heat it again, and bring it back up. Now, air conditioning, how is that done? How do we cool air? Yeah, ventilated. Yeah, but over what? We can't just. Yeah, actually, it's one option, right? If we have cooler outside, we can just use that, and that's in San Diego. We are lucky. We actually often have that option where even in May, June, the air outside is cool enough that you just open the window and you ventilate your room. That's called natural ventilation. But unfortunately, we're not always that lucky, especially in other states. So how do we cool?
Kind of as the name suggests, the condensing unit, doesn't it condense? Like, I don't know what it does, but it condenses something. Which I think it cools down whatever. It like takes in energy from the area around it to do that, and then it heats up like the back part of it and cools down.
Right. Yeah. So as you can tell from the explanation, it's pretty complicated. Right? It's not like you just make a fire and you heat something. Cooling is complicated. Cooling was just invented maybe 50 years ago, and it requires a process where we use pressure and temperature changes to cause air to expand and heat up and then compress and cool it. And then we can magically move heat from the inside to the outside. So we'll discuss in more detail how that works. But those of you who have taken thermodynamics, in thermodynamics you have looked exactly at how these things work in great detail. He will just go over the big picture of how air conditioning units work. Yeah, so that's more complicated, but at the end of the day, it's the same principle in terms of the system. We now use this system, the AC system, to remove heat from this air. So we have hot air coming down, hot air which was heated by the people or by the sun or by infiltration. Hot air coming down, we cool it here, bring it back up as cool air, and so we continually remove heat from the building. Okay, so those were for homes. Now in larger buildings, you need something that's a bit different because there's more concerns about space and about the locality of heating and cooling. So what you often see in hotels is that you have this type of a system on the wall. Right? It's like a bigger box that's usually at the balcony, or it's an outside wall of the room, and you can set there the temperature. You can set the fan flow rate in that. Or in modern hotels, you have just a thermostat, so a little display, and you can control that. And so now the question is, where does the heat and cool come from that's served in this device? And so it turns out this looks like a through-the-wall packaged unit, meaning that it has everything in one place. It's local, but actually it's not. So in hotels, because it's more efficient, since you have, say, you have 200 rooms, so you have 200 of these machines. If you had 200 full-scale, everything in one, all-in-one devices, it would be more expensive and less efficient, because you now have 200 places where you heat and cool things. So rather than doing that, you pipe water around. So you cool and heat water in one place, a big machine, right? It cools a lot of water, heats a lot of water, and then you use that hot and cold water to pump it to these devices. And so now, rather than moving air around, air has a small heat capacity, so we need a lot of air to cool rooms, a lot of ducts, very spacious. Here we just pump water around. It's more elegant. Water is tiny. It's a little pipe, pump it around. You don't need any space for that, so you have bigger rooms for your hotel guests as a result, and you have more efficiency because you do it all locally. So then you plumb the water here, and then this device really just is a heat exchanger, meaning that it's summertime. It takes the cold water, it's coming from the central plant, and then it runs the air from the room over that cold water heat exchanger, and then it brings out cold air. Wintertime is the opposite. Wintertime you have a boiler, so you heat water, bring it up here, and then you heat the room. So in my hotel room adventure a couple of weeks ago, when somebody turned the room to 80 degrees, that's what happened. They basically had this set to 80 degrees, and so the boiler had to produce hot water all the time, which came up to my room. That the thing exchanged the water heat to air heat, and then the room was heated, and then it kept going all day long to heat the room to 80 degrees. So that's very common in hotels. And you see here the central equipment here is the boiler, which is for heating, and then the cooling tower is for cooling. Now in office buildings, commercial buildings, this type of setup is more common. So in this building, we'll likely have also this type of system. So this resembles a bit more what we had seen for the house, in the sense that it has intakes and it has outlets for air for each floor. There's a lot more of those because these buildings are usually larger. So you have, say, 100 different outlets and inlets. But the principle is the same, that you have one supply system and one return system. So in these vents up here, we have some vents that suck in air. We can't see which ones those are. They look the same, but some are only sucking in air, bringing them back to some central room in the building, the mechanical room, and then there it's heated or cooled, humidified, and then it comes back out as fresh air into the space. So here, one thing that's different is that we are mixing air that's coming back, so return air, with fresh air. Typically in residential homes, actually you don't do that. You just rely on the infiltration to provide you with fresh air, and you only worry about cooling and heating the air that's coming back from the house itself. Commercial buildings, they're more sophisticated. Now we have to make sure we perform better in commercial buildings. And so we have here a way to bring in fresh air directly into the system. So we don't have to rely on infiltration, because there is less infiltration in commercial buildings, and we have more people in them, so we need more fresh air than in residential buildings. So that's one thing that's different, is the fresh air control. And so here you have what's called a damper. A damper means you can adjust two sources by moving a metal plate. So either you say close one shaft and open the other one, or vice versa. So you can control what percentage of return air, what percentage of fresh air is entering the fan room here. And the other difference to the hotel setup is that we're actually now ducting the air around. So the water chilling and heating is now more local. It's just happening in the fan room and in the chilled water or boiler, but it just goes to the fan room. It doesn't go to every room. We're ducting the air around the building. Right, and one more anecdote about UCSD. So this is again typical building UCSD. This building is like that. Most other buildings are also like that. Now, do you know where the hot and cold water comes from at UCSD? Nobody? Yep. Cooling towers? Yeah. But where are they? Is it at the building, or is it at each building, or is it somewhere else? Or do you see cooling towers on buildings? Right, that's near the, let's see, where is that? The Eucalyptus Grove, or the so southwest end of campus where Gilman Drive turns, right? That's called the Central Utilities Plant, or CUP. And that's the one place where actually we have a power plant. So UCSD runs its own power plant to generate electricity. But what happens when you do that? What happens when you generate electricity? What do you get as a result? You get electric power and you get heat, right? Lots of heat. So you roughly, just for order of magnitude, we're getting about half heat, half electricity. And so what do you do with that heat? Or what can you do with the heat? You can dump it, right? You can dump it in the ocean, dump it in the air, but that's a waste. So what do we do here? We use that heat to as our heat source. So it's free heat. Right? We don't have to burn any more gas. We have a gas-fired power plant. We don't have to burn any more gas to generate heat. We already have heat. We just take it from the power plant, and now this is basically far away. This is a mile away compared to this building here. So we have basically in the streets all around the campus loop, we have big water pipes that transport the hot water from the central plant to about 300 buildings on campus. So we get free heating for basically free heating for about 300 buildings on campus just from that one source of the power plant. Okay, so that's great, but now I told you in office buildings we don't need much heat, right? You are heating the building, the projector is heating the building. In office buildings, actually, we don't need much heat. We need more cooling. So what do we do there? We only have heat at the central power plant, but we need more cooling. That's what most people don't know. There actually is a way to turn heat into cold. That's called an absorption chiller, which means you take heat, you make cold. And so that's what we do at UCSD. We have an absorption chiller at the central plant. It makes cold water too. And then we now run the cold water also in the same for a separate pipe, but next to each other. One cold pipe, one hot pipe, goes all over campus, goes to each building. And so we also get free cooling from that power plant also. So it's a pretty cool system. There's very few places that have it in the United States. It's called district heating or district cooling, meaning you have one building and one plant in a whole neighborhood, and that provides basically the whole neighborhood with heating and cooling energy from there. The problem is it's gas fired. So in the old days it was great, gas, more efficient than oil, more efficient than coal, but in the last few years, if you've read the news and the Green New Deal movement on campus, they're fighting really hard that we get rid of that power plant, because it clearly emits carbon. It burns methane, so CH4. CH4 turns into CO2. So it's the biggest CO2 source on campus. But on the other hand, it's also very efficient, and it's much cheaper. It saves all of you money, because your tuition would be even higher if we had to switch to, say, buying electricity from SDG&E. So it's a tough battle. I'm not very strongly on either side there. I understand the desire to be ideal here, to have a zero carbon campus, but at the same time, if you take grid power, it's also not carbon free. So really, you're right now at least not making a big difference if you turn off the power plant on CO2 emissions, but you make a big difference on the cost of running the campus. And so there's some ideas for how we could have some compromises. We could maybe use hydrogen to power the plant, but that's still not very proven technology. So we right now just looking at blending, meaning we take some methane, some hydrogen, mix it together, maybe 10% hydrogen, 90% methane. So it's not a big difference, but at least it's a starting point. And maybe in the future, like in 5 or 10 years, then actually have a fully hydrogen powered power plant. Then we would be carbon free, but it would be a big investment to do that. And then you have to now generate the hydrogen somehow, that again may take carbon. Or the other people say, well, shut it down. We'll just cover the whole campus with solar panels and then generate enough power that way. But yeah, there's a lot of issues, economic and environmental to this. So there's no clear best solution to this issue. Okay. Let's talk a little bit more about this zoning discussion that we had in the beginning. So that's HVAC design. So HVAC stands for heating, ventilation, air conditioning. Anybody who works in that field, they will only use that acronym because most buildings need all three. So usually it's one system that does everything. It does heating, it does air conditioning and ventilation. So we always refer to that as HVAC systems. So in HVAC design, so when you're an engineer who designs the HVAC system for a building, you will study all the heat inputs to the whole building, and then you will decide where do you place the vents, where do you define the zones of the building, and then how do you size the ducts so you bring in enough cold air to each room. That's called zoning. Zoning, so you analyze heat inputs and outputs. Separate the building into zones. Then you size the supply air ducts. Okay, so you analyze the heat inputs and outputs, you separate the building into zones, and then you size the supply air ducts. So let's go through each of these steps. So the first step is actually what you have done in the last homework and in previous homeworks. We looked at all the heat that goes into a room. Right? We had internal heat gains, we have heat gains to the wall, we have heat gains to the sun and windows, heat gains to equipment. So these things all have to be analyzed, which means if you plan the building, you're looking already, okay, here's a classroom, here's an office space, here's maybe a dance party room, right? And then you have a table where they can read off, okay, in the classroom, I need to account for per square foot of building space. There are 0.2 students in there, and they give off so much heat. So you can read off, okay, this is the heat source from infiltration, from internal heat gains. And then you use your calculations for the wall resistance, and then you look at every day of the year and say, okay, this is the hottest day of the year, August 20th, the hottest day of the year. This is how much heat will come in from the walls. And so you go through all of these planning stages, and then you figure out, okay, my worst case scenario is I want to keep this building cool on August 20th. And so I have so much heat gain from all of you, from the walls, from the sun. And then I will design my system to be able to remove all of that heat on that worst day. So that means that it will always be cool throughout the whole year. So you do that, and then you figure out, well, given these heat inputs, how do I best split up the building into different zones? So let's look at that. So before we had discussed, we have zones based on occupancy. So we have zones that are busy rooms, like a dance party room versus a classroom versus an office. But we also have zones based on the environment that they're exposed to. So in many buildings you have an exterior space. So you have different offices here. These diagonal lines are doors. So we see here the different offices and doors. And then more here. I won't draw all of them here. So if we have exterior space, that's the space where you have natural lighting coming into the office space. So those are nice spaces. And then we have interior space. So we have a hallway here, and then we have maybe a big meeting room on the interior. Okay, and then we have some orientations here. So we have maybe south is here, north is here. East and west. Okay, so then when we zone this, we have to consider the density of people. AKA how much heat do these people release? Internal heat gain. We also have to consider the activity of people. So, are you sitting? Are you dancing? Why is that? If you dance, you release more heat. And you, when you dance, you want the air to be cooler, to be comfortable. So activities of people goes into the internal heat gain. So that's one element. But what else? What else do we need to consider? How are these different rooms in this building different? Even though we have the same occupancy here. Here's office space. Here's office space. Here's office space. How are these rooms different in terms of how they need to be heated or cooled during the year?
Well, seasons obviously, but then based off where the sun rises and sets, or based off where other buildings are placed around it, it may get more sun into it and just naturally heat up.
Yeah. So the answer was because of the sun position. The sun will rise in the east, and then we'll go to the south. Go to the west. In this class we'll actually look at that also, but it's something that's intuitive to most of you because of you see it every day. You have seen it every day. So that means that in the morning the sun is over here, right? At midday it's over there, and then evening there. So, but what else matters about the sun? So one thing is the horizontal position, but what else matters about the sun in terms of how much heat you get into these rooms? So south, east, west. Yep.
the south side always receive most solar radiations?
Huh? Yeah, south side receives the most radiation. That's because on average the sun is there the most time, right? So winter time actually the sun is very little in the east. It rises about here. So only an hour later or 2 hours later, it will no longer actually shine any light into this space. It will only be on the south side, for many hours, and then just be a little bit on the west side. Yeah. Yeah, that's right. We're ignoring the southern hemisphere here. So yeah, thank you. We're only looking at the northern hemisphere. So the southern hemisphere, of course, you're looking at the north side being the bad side, in say Australia or most of Africa. Okay, what else matters about the sun? We have the horizontal position, but what else matters about the sun?
The season?
Yeah, how does it affect the?
Yeah, I think. It would probably be. It would have vertical position.
Yeah, the vertical, right? So that's called the elevation angle of the sun. So the vertical position. So in winter time, sun is lower, which is bad for us walking because the sun is in our eye more. We get blinded more by the sun. In summertime, it's higher. But what's nice about lower sun in winter is that it gives more heat into the room, right? Because the sun is horizontal ideally. It shines at a very high density into the room. Sun is vertical. It does not shine in the room at all because the rays are parallel. So that means the elevation also matters, which means that when the sun is in the east and west, actually it's lower. So it will provide more heat input. If the sun is in the south, it's higher, and so it will provide less heat input. Yeah, so we can see that the seasons matter, the time of day matters, and how these offices are heated. So if we were to apply the same amount of cooling to each space, it would be bad, because in the afternoon, these offices will be really hot, and these will be too cold, vice versa. So now that means to zone this properly, you usually cut off the different aspects or sides of the building to create separate zones here. So basically one zone would be the south side, and then one zone would be the east side, and on the north side, and so on. Out of colors, so the black here. So we are zoning by what's called the aspect or direction. Then we still have the interior space, and that's again different, right? Because interior space never gets sun. And that means it will need the least cooling from that standpoint. So it has to be its own zone also. That means that in this typical layout, you would have at least 5 zones for every floor, one interior zone, and then one zone for each of these spaces. But there may be more zones, because if the occupancy also is different, like a classroom here and offices, then you can split those up into different zones. Because of the occupancy in that room. So here we'll have 5 zones per floor based on the direction the zone faces. East, west, south, and north. And then central. Right, so that's zoning. Then let's look at the local versus non-local types of systems. Local versus non-local HVAC systems. So what's a local? What's a local system? That's your self-contained or packaged or all-in-one unit where you have heating, ventilation, and air conditioning all in one space. So it's a packaged or through the wall. Unit. So through the wall may also mean through the window. It's the same principle. Window, it's typically easier because you can retrofit it. If you put it through the wall, you have to cut the wall open and seal it and so on. Depending on how the building was built, you may only have the option of putting it through the window. But the principle is the same, that you stick this through the wall. Here's your room, your building. And now you have inside here heating, cooling, and ventilation. All in one box. So we have heating, cooling, ventilation all in this box. So that's one option, and the other option is that we have a central or non-local. Central or non-local. System. That's the case where we run the air through the whole building. So we have some outlets, some inlets. So now we have in one place in the building, in one central place, we have one box here that also does everything. Does heating, cooling. It doesn't do everything. It does not do ventilation. It just does heating and cooling because there's no fresh air in the basement. So heating and cooling from this central location. So in the first case, we would need several of these to achieve the same effect as here, right? Because we have, in this case, we have 2 rooms in the house, then we would need two through the wall units in this case to separately supply these 2 rooms with heating, cooling, ventilation. Right, so let's think about possible advantages and disadvantages of these different types of systems. They both exist a lot, right? There's many buildings who have these through-the-wall units. There's many buildings who have this type of system. What are some benefits of each solution? Benefits of the local versus the central. Okay, so any guesses what could be an advantage of the local system?
Well, the zoning is easier in local system.
Yeah, so the zoning is easier in local systems. That's right. Each local system is by default in its own zone. Right? It's disconnected from the other system, so we can set this to 90 degrees and this one to 60 degrees. It works just fine. In the central system, as I mentioned before, while you could zone it in theory, in practice it's usually not zoned. And once it's not zoned, it's a nightmare to convert it to zoning. So this means in this case you're wasting energy because you're cooling places that don't need to be cooled, and vice versa. So the local one is easier to zone. So you can adjust the cooling or heating to the local needs. Central is often not zoned and wasting energy. Because we're cooling, heating in places where we are not even there. Heating of unoccupied areas. And we have some rooms that are too cold, others are too warm. So we have uneven heating. Okay, so that's an advantage of the local system. It's more specific to the area that we want to heat or cool. What else? Yeah.
Does the central one depend less on the say the temperature of the outside air around it? It just kind of uses like electrical energy just to cool or heat air as it needs.
So the point was, does the central one depend less on the air around it? Yes, and it's in a way that you actually have more infiltration with this type of system, because you're now creating more gaps in the wall, so you have more potential for air to come in and out of here, because it's another way to make the envelope of the building more penetrating than in this system. So here you're creating some inefficiency because you have more infiltration. That's going to happen. So more infiltration. Through gaps in the wall. You get less infiltration. Yep.
By uneven heating and cooling for central, do you mean you can't account for internal heat generation?
Yeah, that's one reason. But so if you have one room that has all your friends in it, right? You're having a big party, then I would not be able to distinguish the cooling needs for that room versus say a bedroom that's unoccupied. Yeah, but it could also be because of weather. So it could be the sun shining in one, like in the highest floor being hotter than the coldest floor. Yep.
Generally, or at least what I've dealt with for the ones on the left here, you plug them into a 120 volt wall outlet, like in your room. You know what you have in a room, and usually they max out the circuit, so there's not much else you would be able to plug into the same circuit. Whereas the central one usually goes into 240 volt or higher with a higher amperage that it can contain, and then goes to electrical panel with its own breakers. So
yeah. So the answer was that electrically, this is really plugged in the wall. And unless the home was built to have a system like that, which is often not the case, you only have a regular 110 volt outlet, and so that has limited capacity for cooling and heating, which means you may actually not be able to cool your room on the hot days because there isn't just enough power there to do it. Whereas in this case, when they planned the home, they sized the place where the heating cooling is appropriately, so it has 240 volt outlet. So you can generate more power. So one point is that heating cooling takes a lot of energy. So that's the most energy intensive appliance you have in your whole house. It's more energy intensive than the water heater, more than the stove. and anything else. So that's why the power supply to this equipment is very important too. Yeah, so let's write it down. Local may have limited power. So usually you have a 110 volt outlet. Then you're limited to having 20 amps of current on this. So then basically you have about only 2 kilowatts of power. Whereas here, these are usually sized larger. We have enough power. So we have limited cooling. Limited cooling and heating capacity for the local systems. And here we have enough power for the central systems. So you may have 240 volts. You may have a 40 amp breaker. You may have 10 kilowatts of power here. So you have sufficient cooling for the whole year. Question?
Well, I wanted to say, like, maybe a pro for central is like per BTU of actual heat moved, it's probably more efficient than a bunch of tiny units.
Oh, I already passed the hour, sorry. Yeah, good point. So last point here was that it may be more efficient, a central unit, and that's right, because we can build larger systems to be more efficient than smaller systems, where you have to be more compromising on how you route things and how you insulate things. So bigger systems are more efficient. Yeah. Right, we'll finish this off next time. Thank you.